A gravitational field is a region around one mass which affects other nearby masses. It is very weak, however, which is why the effect is only significant on large objects like the Earth. We can represent the Earth's gravitational field by drawing field lines showing the direction of the gravitational force on masses in the field. In this case, the field is radial and equally spread around the Earth. On the surface of the Earth, the gravitational field is approximately uniform because the field lines are virtually pointing in the same direction and are equally spaced. This is why we assume the acceleration due to gravity is a constant of 9.81 meters per second squared, because the change at small vertical heights is negligible. Newton's law of gravitation states that all masses attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between the centers of mass. This gives us the equation F equals minus gmm over r squared, where g is the universal gravitational constant of 6.67 times 10 to the minus 11, m is the mass of the larger body, m is the mass of the smaller body, and r is the distance between the centers of mass of the two bodies. The minus sign simply refers to the fact that the force is attractive. For example, two bodies, one of mass 6 kg and the other of mass 20 kg, are placed 50 cm apart. From this we can work out that the gravitational force acting on each object is 3.20 times 10 to the minus 8 newtons. The force acting on each body is equal because they are attracted to each other. The gravitational field strength is the force per unit mass at a point in a gravitational field. For a uniform field, the equation is G equals F over m, where F is the force experienced by the body and m is the mass of the body. For a radial field, the gravitational field strength obeys an inverse square law. The equation for it is G equals gm over r squared. You can see how the gravitational field strength would decrease the further you are from the center of the body producing the field. This formula can be used to work out the masses of celestial bodies. For example, given that the gravitational field strength on the Earth's surface is 9.81 newtons per kilogram and the radius of the Earth is 6,400 kilometers, we can work out the mass of the Earth to be 6.02 times 10 to the 24 kilograms. When considering planetary motion, the gravitational force acting on the body orbiting is equal to the centripetal force because the force acts perpendicular to the direction of motion. By equating the two formulas and using the formula for the speed of an object in circular motion, we get the equation t squared equals 4 pi squared over gm r cubed, where t is the orbital period in seconds, and r is the distance between the centers of mass of the orbiting body and the body being orbited. This equation shows Kepler's third law, which states that t squared is directly proportional to r cubed. This also suggests that for a set of celestial bodies, e.g. the planets of our solar system, orbiting the same large body, e.g. the Sun, t squared over r cubed is a constant and is equal for all the celestial bodies. For example, given that it takes 365 days for the Earth to orbit the Sun, and that the distance of the Earth from the center of the Sun is 1.5 times 10 to the 11 meters, we can work out the mass of the Sun to be about 2 times 10 to the 30 kilograms. Given that the orbital period of Mars is 687 Earth days, we can use the Earth's orbital characteristics to work out how far Mars is from the Sun, as being 2.29 times 10 to the 11 meters. A geostationary orbit is an orbit around the Earth whose orbital period is 24 hours. They are located above the equator and are always vertically above the same point on the surface of the Earth. This makes them useful for TV satellites because the dishes can be pointed to a fixed point in the sky, which is quite convenient, I'd say.
Electric field strength is the electrostatic
force acting on a unit.
Positive test charge placed at that point if F bar is the electrostatic force experienced by a test charge Q at a point, then the electric field intensity at that point is given by E bar is equal to F bar by Q. A SI unit of electric field intensity is Newton per Coulomb. Note: if the test charge is not small, then the electric field may be affected by the test charge, and hence we modify the above equation as follows. E bar is equal to limit Q tends to 0, F bar by Q. Subtopics: electric field due to a point charge, electric field due to a system of charges, physical significance of electric field. Electric field due to a point charge. Consider a charge Q at the origin of the coordinate system. Let a test charge Q be placed at a distance r from the origin. If F bar is the force exerted by Q on Q, then according to Coulomb's law, F bar is equal to 1 by 4 pi epsilon naught Q by r square r cap. Equation 1. If r cap is a unit vector in the direction of r, electric field E bar is equal to F by Q. E bar is equal to 1 by 4 pi epsilon naught Q by r square Q r cap. E bar is equal to 1 by 4 pi epsilon naught Q by r square r cap. The magnitude of the electric field intensity due to a point charge is E is equal to 1 by 4 pi epsilon naught Q by r square. Electric field due to a system of charges. Consider a system of charges Q1, Q2, and so on, Qn, placed at distances r1, r2, and so on, Rn, with respect to some origin. Then the electric field intensity due to all these charges at a point is found out using the principle of superposition. Let E1 bar, E2 bar, E3 bar, and so on, En bar be the electric field intensity due to the number of charges Q1, Q2, and so on, Qn. Then the resultant electric intensity E bar at that point due to these charges is given by the superposition theorem. E1 bar is equal to E1 bar plus E2 bar plus E3 bar plus, and so on, En bar. Electric field intensity due to the nth charge is En bar is equal to 1 by 4 pi epsilon naught Qn by Rn square r cap. Magnitude of the electric field intensity is given by the equation En is equal to 1 by 4 pi epsilon naught Qn by R.
A is magnetic field.
You are late again. Hurry up. Something is wrong.
The region surrounding a magnet in which the force of the magnet can be experienced is called its magnetic field.
Seems like a nice spot to relax. It's an alien ship. We must be careful. Run!
Take a bar magnet and keep it on a table.
Wow, such a colorful spacecraft. Let's go there. Activating transparent sheet.
Keep a transparent sheet on top of the magnet. Now, take some iron filings. And sprinkle them on the paper.
Arrange yourselves properly.
The iron filings will start arranging in a definite pattern around the magnet. This pattern is called a magnetic field. The lines along which the iron filings arrange are called magnetic field lines. The magnetic field lines show the direction and strength of the magnetic field. Magnetic field lines always start from the North Pole of the magnet and end at the South Pole. Inside the magnet, their direction is from the South Pole to the North Pole. Thus, the field lines form closed loops. Field lines never cross or intersect each other. The closeness of the magnetic field lines tells us about the strength of the magnetic field in that area. The more closely packed lines indicate a stronger magnetic field. Therefore, we can see more iron filings sticking at the poles. As the lines spread out, the magnetic field weakens.
Why did I come here?
That was the best time of my life.
You had an amazing experience.
Yes, I miss my friends.